A retreating army could turn a river into a weapon with one demolition charge. The bridge collapsed, the road ended, and every truck behind the advance began consuming supplies without moving them forward. For German planners, destroyed crossings promised something increasingly rare in 1944. Time then, Allied engineers arrived, carrying pieces of another bridge. They needed no custom-built girders. Massive floating cranes or permanent concrete foundations, they brought standardized steel panels, pins, rollers, wooden decking, and a design that could grow stronger by repeating itself. A wrecked crossing was still dangerous, but it was no longer guaranteed to stop an army for long. The Germans could demolish the bridge in front of the Allies. What they struggled to demolish was the system waiting behind it. How could one ordinary steel panel transform calculated destruction into a temporary interruption? The answer began far from the rivers of France, Italy, Burma, and Germany. It began with a British civil servant named Donald Bailey and a deceptively modest design problem. Military bridges already existed, but wartime movement demanded a harsher combination of qualities. A bridge had to travel on ordinary vehicles. Its pieces had to be manageable without specialized lifting equipment. Different factories had to manufacture components that would still fit together at the front. The same basic inventory had to cross narrow gaps, wider rivers, and loads ranging from light vehicles to tanks that normally required several different bridges. Bailey's solution was not one miraculous structure. It was a modular language. Its defining component was a rectangular steel truss panel, 10 feet long, joined to the next panel with large pins. Engineers could place panels side by side when a heavier load demanded more strength. They could stack another truss above the first when the span demanded greater stiffness. Transoms connected the two sides. Stringers and wooden decking created the roadway between them. The bridge changed capacity without changing its basic vocabulary. That mattered because battlefield engineering was not performed inside a controlled factory. It happened beside damaged roads. Under uncertain weather, with exhausted men and an enemy nearby, a component that required individual fitting could delay the entire crossing. A standardized component could be identified, counted, replaced, and assembled according to a familiar drill. The humble panel therefore carried something larger than steel. It carried predictability. Britain began delivering the bridge to troops after an unusually rapid development and production effort. Its manufacture was distributed among firms working to common dimensions. The system was then shared across Allied forces, including American, Canadian, Indian, Australian, and other engineering units. This was coalition warfare expressed through holes, pins, and interchangeable parts, yet the bridge's most important feature appeared only when engineers met a real gap. They commonly assembled the trusses on the near bank, where men and equipment had some protection. A lightweight launching nose extended ahead of the bridge. The completed structure was pushed across rollers toward the opposite bank. The nose reached the far side first and helped guide the heavier roadway into position. Instead of building outward while suspended above the obstacle, engineers could construct much of the bridge on solid ground. The method did not remove danger. Work sites remained exposed to artillery, mines, floods, damaged approaches, and sudden changes in the river. Nor could every gap accept the same arrangement. Foundations still mattered, banks still collapsed, loads still had limits. But the design separated many recurring problems from the unique geography of each crossing. The approaches might be improvised. The central components remained familiar. That distinction changed the tempo of repair. A German demolition party could study one bridge and calculate how to destroy it. The Allied response did not have to recreate what had been lost. Engineers could replace its function with a structure already divided into transportable, rehearsed modules. And once traffic resumed, the temporary bridge did not always remain there. Engineers could replace it with timber or a more permanent crossing, dismantle the Bailey, and send its panels forward again. The same steel could solve the next interruption. That was the first hidden mechanism. Germany was destroying locations. The Allies were circulating capability. The difference would become visible in Normandy, where rivers, canals, bomb damage, and demolished roadways repeatedly cut across the advance. There, the Bailey Bridge would stop being an ingenious British design. It would become part of a moving industrial network. Normandy tested the system before the Allied armies had room to move quickly. The landscape was crowded with narrow roads. Sunken lanes, streams, canals, railway embankments, and villages reduced to rubble. Bombing had damaged transportation routes intended for Allied use as well as German movement. Retreating troops demolished additional crossings behind them. Every broken span created two simultaneous battles. Infantry and armor fought for the far bank. Engineers fought to connect that bank with fuel, ammunition, ambulances, recovery vehicles, and reinforcements. Capturing ground without restoring traffic could leave the attackers holding an isolated prize. The first vehicles across were not necessarily the heaviest. Assault boats, rafts, or surviving fragments could move infantry over a gap, but a bridgehead consumed material immediately. Riflemen needed ammunition. Wounded soldiers needed evacuation. Anti-tank guns had to arrive before a German counterattack. The tactical clock, therefore, ran faster than the construction clock. Bailey equipment helped compress the difference. Panels traveled forward in organized bridge loads, accompanied by the pins, transoms, rollers, ramps, decking, and tools required to assemble them. Truck drivers had to recognize each component and deliver it in the proper sequence. Depot crews had to count pieces that appeared identical but served different configurations. The bridge was modular, but the supply chain supporting it could not be careless. A missing pin was physically small. At the wrong moment, it could immobilize tons of steel. That made training extend far beyond the engineers standing beside the river. Quartermaster and transportation units learned the unfamiliar vocabulary of bridge parts. Drivers learned how the loads were arranged. Depots moved forward in stages, issuing components while repairing floats and recovering reusable equipment. The bridge speed depended upon this largely invisible organization. In July 1944, American engineers encountered damaged crossings around the Vire and the approaches to St. Lo. At Le Miof, the 234th Engineer Combat Battalion reached its work site close behind the infantry. The men erected a Bailey Bridge, a treadway crossing, and a bypass for traffic around a weakened railway overpass. The structures did not represent a single universal answer. They formed a layered response to different vehicles, loads, and routes. This was how the system operated in practice. The Bailey handled one requirement while treadway equipment and repaired roads handled others. Military traffic was divided so that one fragile point did not carry every burden. Engineering was becoming traffic management as much as construction. Days later, near Pont Hébert, the same battalion faced another damaged transport corridor. A floating treadway bridge was completed first. A Bailey followed later that day, giving the route another way to carry movement across the obstruction. The important detail was not simply that engineers built quickly, it was that recognizable components. Practiced crews, transport units, and several bridge types could be recombined around the damage actually found. German demolitions remained tactically effective. They forced reconnaissance, clearance, construction, and exposure. They consumed hours, and sometimes days that the Allies wanted desperately to save. But each demolition also entered an enemy system designed to classify interruptions and assign equipment against them. This was not invulnerability, it was regeneration. When permanent materials became available, engineers often replaced a Bailey with a timber bridge. They then dismantled the steel structure and moved it toward the next river. The bridge behaved less like a building than a reusable tool. A panel used near one Norman village could become part of another crossing farther east. That circulation changed the mathematics of retreat. German forces could destroy a different structure at every river. The Allies did not require a different industrial response for every ruin. They needed another suitable configuration of familiar parts. Yet Normandy also exposed the limits of rapid bridging. Vehicles packed tightly behind a crossing formed vulnerable queues. Mud weakened approaches. Artillery could strike men working in the open. A bridge completed on schedule still failed strategically if traffic control collapsed on either bank. The steel panel was only the visible center of a larger mechanism. Reconnaissance selected the site. Trucks delivered the correct loads. Engineers assembled and launched the structure. Military police controlled the approaching columns. Maintenance crews kept vehicles from blocking the roadway. Then another unit recovered the bridge when the route no longer needed it. By itself, the panel did nothing. Inside that chain, it converted industrial standardization into operational speed. The Allied breakout from Normandy would stretch this mechanism much harder. Once the armies began racing across France, Broken bridges were no longer isolated engineering problems. They became tests of whether an entire supply network could keep pace with victory. The breakout transformed distance from an objective into an enemy. Allied columns advanced faster than planners had expected, leaving supply dumps, repair shops, and functioning railheads far behind. Fuel traveled hundreds of miles by truck. Every detour increased consumption, vehicle wear, congestion, and driver fatigue. A destroyed bridge now threatened not one crossing but an entire timetable. The Seine presented the first major test of pursuit warfare. German forces withdrew across the river while demolishing bridges and attempting to establish another defensive barrier. Allied troops reached the banks before their logistical structure had fully recovered from the advance. The river was wide. The pressure to cross was immediate. Engineers used assault boats and rafts to establish bridgeheads, then began creating heavier connections. Pontoon equipment carried vehicles, while Bailey components supplied more durable routes at selected sites. The crossings required engineers from several Allied armies, disciplined traffic control, and constant movement of bridging stores toward the river. The design's flexibility became crucial. A Bailey could rest on fixed supports, span a destroyed section, or connect floating structures to unstable banks. At ports, versions of the bridge could even rise and fall with floating piers as the tide changed. It was not merely a replacement for a demolished road bridge. It was an adaptable connection between surviving fragments of infrastructure. This flexibility also produced an important strategic illusion. To a commander studying a map, every river appeared as a clear defensive line. On the ground, its value depended upon time. Could the defender destroy the crossings? Could he cover the banks? Could the attacker bring forward boats, bridging equipment, engineers, and traffic control units before resistance stabilized? The river itself answered none of those questions. The surrounding systems did. German demolition orders therefore produced uneven results. A bridge destroyed too early could trap friendly troops and equipment on the wrong side. A bridge destroyed too late might be captured intact. A perfectly executed demolition could still lose much of its value if Allied engineers rapidly opened another route nearby. The contest was not between explosives and steel, it was between two clocks. The retreating forces needed interruption long enough to reorganize. The pursuing forces needed restoration before fuel and ammunition shortages slowed their momentum. The Bailey Bridge repeatedly shortened the interval that demolition was expected to purchase, but it could not erase geography. In the Netherlands, Operation Market Garden exposed this boundary with brutal clarity. The Allied plan depended upon a narrow road crossing a sequence of waterways. Airborne troops were to seize bridges while the ground column advanced along the same corridor. Every missing crossing threatened everything scheduled behind it. At sun, German troops destroyed the road bridge across the Wilhelmina Canal as American paratroopers approached. The local tactical success of taking the area did not restore the route. Heavy vehicles still could not cross. British engineers brought Bailey equipment forward through the congested corridor and worked through the night. The replacement bridge opened the next morning. That achievement demonstrated the modular system at its most useful. A demolished crossing had been replaced quickly enough for the advance to continue. It also demonstrated the limit of calling any bridge a miracle. The delay had already affected movement along a plan with almost no spare time. Traffic accumulated. Units scheduled farther north waited for the road to reopen. The bridge solved the physical gap. It could not recover every lost hour farther along the corridor. Resistance, congestion, communications failures, and the inability to secure the final bridge at Arnhem overwhelmed the operation. No standardized panel could repair a plan whose risks extended across the entire route. This distinction matters. The Bailey Bridge did not make waterways irrelevant. It changed the price and duration of certain interruptions. Its success depended upon equipment arriving, engineers surviving, approaches remaining usable, and the far bank being held. Where those conditions failed, the system slowed or stopped. Where they held, demolition became less decisive than German planners needed it to be. That created a widening imbalance. The German army was losing transport, fuel, bridging equipment, trained specialists, and freedom of movement. The Allies were carrying reusable bridging inventories inside a larger supply network. One side increasingly relied upon each demolition to produce maximum delay. The other could accept damage, classify the gap, and begin assembling a known response. After the Netherlands, the Allied advance paused, for reasons no bridge could solve alone. Ports had to be opened, railways required repair, fuel routes had to be shortened. Winter approached, then Germany launched its Ardennes offensive and once again made bridges central to its calculations. This time, German forces would discover what happened when their own timetable depended upon capturing crossings intact. The Ardennes offensive reversed the familiar problem. German armored columns were now advancing toward rivers. While Allied forces withdrew, defended crossings, and prepared demolitions, the German plan depended upon speed, captured fuel, usable roads, and bridges over the Meuse. A delay at any one point would magnify shortages everywhere else. This was the same mathematics German demolitions had imposed on Allied armies, but the German system had less capacity to absorb failure. Narrow roads became blocked by wrecked vehicles and confused columns. American resistance delayed access to key junctions. Fuel consumption continued while spearheads searched for open routes. Bridges that existed on operational maps remained beyond German reach. The offensive demonstrated the difference between possessing powerful vehicles and sustaining their movement. A tank could defeat another tank and still become useless without fuel, maintenance, road space, or a crossing strong enough to carry it. The German attack did not fail because of one missing bridge: resistance, logistics, Allied air power, command decisions, and inadequate reserves all contributed. Yet the attempt revealed how strongly operational success depended upon connections that could not be improvised at the required scale. When the Allies resumed their advance, they approached Germany's major rivers with the same lesson. The Rhine was not simply another obstacle. It was broad, fast, industrially significant, and embedded in German expectations of final defense. The bridges across it were obvious demolition targets. On the maps, their destruction promised a strategic pause at Remagen. That expectation fractured. American troops approaching the Ludendorff Railway Bridge found it still standing. German demolition charges detonated, but the span did not fall. Soldiers crossed while fighting continued around the eastern end. The capture created an opportunity no operational schedule had guaranteed. Commanders immediately chose to exploit it. Men, vehicles, artillery, and supplies began moving over the damaged bridge. Engineers worked to keep the structure usable while German forces tried to destroy it. Artillery fire, air attacks, floating explosives, and other attempts threatened the crossing and the growing bridgehead. The railway bridge was valuable precisely because it already existed, but relying on one damaged structure would have turned opportunity into vulnerability. The Allied response was therefore not merely to celebrate its capture. Engineers created additional crossings. Treadway and pontoon bridges began carrying traffic across the Rhine. A heavy Bailey bridge added another route to the bridgehead. Each new crossing reduced dependence upon the failing railway span. This was system behavior. The intact bridge opened the door. Standardized bridging prevented the entire operation from depending upon that door remaining open. 10 days after its capture, the Ludendorff Bridge collapsed. 28 American engineers were killed. Others were injured. The loss exposed the human cost hidden inside the language of rapid repair. Engineers had worked on a damaged structure under enemy attack and relentless traffic. Their task was logistical, but their workplace was a combat zone. The collapse did not erase the bridgehead. By then, alternative crossings were operating, and forces had accumulated on the eastern bank. The original bridge had enabled the first surge. The network of replacement routes preserved the result. Farther north, British and Canadian formations prepared a much larger planned crossing of the Rhine. Their operation required assault craft, amphibious vehicles, ferries, pontoon bridges, Bailey equipment, road construction, smoke, artillery, and traffic control. No single bridge type carried the entire burden. Different crossings served different load classes and stages of the movement. Canadian engineers helped build Blackfriars, a long Bailey pontoon bridge near Rhys. Other British and Canadian units constructed additional bridges around Rhys and Emmerich at Emmerich. Engineers began work on the low-level Melville Bridge after the area was secured. Wind complicated the handling of floating sections. Minefields had to be cleared from the northern bank. Nevertheless, the bridge opened the following evening. Traffic then moved across it continuously. This was not improvisation replacing planning. It was standardized equipment allowing detailed planning to survive unpredictable conditions. The river, wind, mines, damaged roads, and changing water levels could not be standardized. The response could. By the spring of 1945, German forces were no longer confronting isolated bridges. They were confronting a coalition able to build several kinds of crossings, assign them by load, and feed them from an immense transport network. Demolitions still destroyed steel and stone, but it increasingly failed to create the strategic pause Germany needed. The temporary bridge had become part of a permanent Allied advantage. The Bailey Bridge, a strategic meaning becomes clearer when the camera moves away from the Rhine. The same family of components appeared in Italy, where steep valleys, mountain rivers, floods, and demolished roads punished every supply column. It appeared in Burma, where monsoon conditions and difficult terrain placed enormous pressure on transport. Its geography changed. Its industrial logic did not. In Italy, engineers frequently confronted gaps whose approaches were as difficult as the rivers themselves. Mountain roads restricted trucks and construction equipment. Rain turned working areas into mud. Retreating German forces destroyed bridges, culverts, and road surfaces while preparing positions farther north. A replacement crossing could reopen one route, only for the next landslide or demolition to close another. Bailey components gave British, American, Canadian, South African, Indian, New Zealand, Polish, and other Allied formations access to a shared engineering solution. The coalition still used different vehicles, organizations, and supply procedures. Local conditions still demanded adaptation. Yet the bridge offered a common physical vocabulary that could be taught, transported, and repeated. Some units became bridge specialists through necessity rather than long preparation. Transport and service formations learned to load unfamiliar components. Depots leapfrogged forward behind combat units. Crews repaired floats and recovered bridge equipment from flooded or abandoned sites. The system depended upon labor rarely visible in photographs of completed crossings. Men sorted steel in depots. Drivers carried awkward loads along damaged roads. Mechanics kept cranes and trucks running. Engineers checked pins, supports, and load arrangements while traffic waited behind them. The famous bridge was the final assembly of all that hidden work. Burma imposed another variation. Road networks were sparse. Rivers and seasonal watercourses repeatedly interrupted movement. The Allied campaign relied upon multinational forces operating across long and difficult supply routes. Bailey bridges could be transported as components and assembled where permanent civil infrastructure was absent or destroyed. Floating configurations carried traffic where fixed supports were impractical. Again, the bridge did not conquer terrain by itself. Road builders, labor units, local workers, boat crews, transport formations, and combat engineers created the route around it. This wider record prevents one misleading conclusion. The Bailey Bridge was not proof that craftsmanship no longer mattered. Its success required skilled judgment at every site. Engineers had to assess banks, current, span, load, alignment, anchorage, and launching conditions. Incorrect assembly or an unsuitable configuration could produce failure. Standardization did not replace expertise. It allowed expertise to act faster. The design moved part of the problem from the riverbank into the factory and training ground. Dimensions had already been fixed. Connections had already been tested. Load arrangements had already been calculated. Crews arrived with established construction methods rather than beginning with a blank sheet beside every crater. That is where the industrial advantage entered the tactical scene. Factories produced interchangeable parts. Shipping and rail systems moved them toward theaters of war. Depots reorganized them into bridge loads. Trucks delivered those loads to engineer units. Engineers configured them for the gap. Traffic control personnel turned the completed structure into a functioning route. Information and material moved through the same chain. Reconnaissance described the obstacle. Headquarters allocated bridging equipment. Depots released the components. Drivers moved them forward. Engineers created the crossing. The effect appeared later in fuel tanks. Ammunition stocks evacuated wounded and armored vehicles arriving beyond the river. The bridge was therefore both an object and a message. It told retreating German forces that destroying infrastructure would impose costs, but might not reset the campaign. The next defensive line could receive less preparation time than expected. Units withdrawing toward it could find Allied reconnaissance already approaching. A local demolition might succeed completely and still fail operationally. The Allies paid heavily for this capacity. Engineer casualties were real. Production consumed steel, timber, factory labor, shipping space, and fuel. Bridging convoys competed with ammunition, food, medical supplies, and replacement vehicles. A panel sent to one corps could not simultaneously serve another. Traffic across a temporary bridge remained slower and more vulnerable than movement across an intact permanent structure. The system reduced friction. It never abolished it. Its deeper strength was regeneration. A damaged route triggered a response that had been anticipated industrially, organized logistically, and rehearsed technically. Once a permanent crossing replaced the temporary one, the panels could be recovered. The solution did not disappear after performing its first task. It returned to inventory. It moved forward. It waited for the next demolition. That repeated cycle turned a temporary structure into a strategic asset. Germany could keep creating gaps. The Allied system kept converting selected gaps back into roads. By the final weeks of the war in Europe, the Bailey Bridge had become almost visually ordinary. Archival photographs show trucks crossing narrow steel roadways above rivers filled with wreckage. Other images show engineers working among twisted girders, broken masonry, and damaged embankments. The scenes appear improvised. The components were anything but improvised. Each familiar panel represented drawings, tolerances, factory schedules, inspections, transport manifests, depot inventories, and training completed before that particular river became urgent. That preparation explains why the bridge could appear wherever urgency demanded it. It also explains why simple production totals cannot capture the advantage. A warehouse full of panels was not a crossing. The panels mattered only when the correct components reached a surveyed site in useful order. They mattered when engineers knew which configuration could carry the expected traffic. They mattered when another unit prepared the approaches and military police prevented congestion from freezing the route. The system succeeded at the point where standardization met coordination. German forces possessed capable military engineers and repeatedly built or repaired crossings under severe conditions. They also improvised with local timber, captured equipment, boats, and surviving civil structures. The difference was not intelligence or courage. It was the shrinking material environment in which German engineers were forced to work. Fuel shortages restricted movement. Allied air attacks damaged railways, roads, factories, and transport vehicles. Retreat consumed bridging stores faster than they could be replaced. Different fronts competed for diminishing resources. An engineer could understand precisely what a crossing required and still lack the trucks, fuel, steel, time, or protected workforce needed to create it. That was the system collapse behind the visible battlefield. The bridge itself was only one indicator. Allied forces could lose vehicles, bridges, and equipment while retaining the capacity to replace their function. Germany increasingly lost not only objects, but the networks that made replacement possible. A demolished span therefore carried opposite meanings for the two sides, for the defender. It was a calculated withdrawal of infrastructure. For the attacker, it was a request sent backward through a prepared engineering system. The outcome depended upon which organization could complete its next process first. Sometimes the demolition won valuable time. Sometimes mines, fire, floods, or congestion extended that delay. Market Garden proved that even a quickly completed Bailey could not rescue an operation from failures elsewhere. Remagen proved the opposite point. When an accidental opportunity was supported by redundant crossings, the loss of the original bridge did not reverse the strategic result. Both cases warn against turning equipment into legend. No bridge shortened a war by itself. People selected the site, transported the parts, assembled the steel, regulated the traffic, and defended both banks. Some performed that work under shell fire. Some were killed while maintaining structures already celebrated as successes. Others labored in factories, ports, rail yards, depots, and truck columns far beyond the camera's frame. Their combined effort gave the object its power. After the war, Bailey bridges did not vanish with the armies that had carried them. Surplus components replaced damaged civil bridges in countries struggling to restore roads and communities. The design continued serving after floods, earthquakes, and other emergencies. Later modular bridges inherited much of its central idea. Small standardized components could be transported rapidly and configured for different gaps. A wartime expedient became a durable method of reconnecting damaged landscapes. That post-war life reveals something important about the original design. The Bailey was not optimized for one famous battle. It was optimized for recurring uncertainty. Its builders could not know the exact width of every future gap. They could not predict which stone bridge would survive bombing or where a retreating force would place explosives. Instead, they standardized the response while leaving the final configuration flexible. This was industrial warfare at its most consequential. Not a single enormous machine, but a family of parts that could be assembled by trained people into whatever strength the moment required. Return now to the first destroyed bridge. The blast tears through the span. Steel folds into the water. The road disappears, and the retreating force gains several precious hours. Behind the advancing troops, however, reconnaissance reports the gap. A headquarters assigns bridging equipment. A depot releases organized loads. Trucks carry panels, transoms, rollers, decking, and pins toward the river. Engineers prepare the banks and begin assembling a replacement on solid ground. The lightweight launching nose moves over the void. Then the heavier structure follows. Traffic starts again. Fuel crosses. Ambulances return. Artillery and reinforcements move toward the next line. The demolition was real. The delay was costly, but the interruption did not become permanent. That was the quiet strategic power contained inside one 10-foot steel panel. Germany could destroy a bridge. The Allied system had learned how to move the idea of a bridge from one river to the next, and in a war of retreat against regeneration, the reusable idea proved harder to stop than the structure itself. If you value documentary stories about the systems behind victory, subscribe for the next investigation.